Okay, so get this. We're diving into a theory today that even made Einstein scratch his head a bit scalar-tensor theory. You sent us this excerpt from the scalar-tensor theory of gravitation, wondering how it challenges everything we thought we knew about gravity. It's like this excerpt is written in a completely different language, right?
Yeah, it can definitely feel that way.
But don't worry, we've got you covered. We're basically going to translate some seriously complex theoretical physics into something that won't make your head spin. Hopefully.
We'll do our best.
So everyone knows Einstein, yeah? The guy who basically flipped our understanding of gravity on its head. Said it's all about space-time being warped, curved, all that jazz.
Right, space-time tells matter how to move, and matter tells space-time how to curve.
Exactly. But what if, and this is a big what if, he wasn't 100% right, what if there's more to gravity than just this curvature?
That's where this whole scalar-tensor theory comes in.
You got it. It throws this extra ingredient into the mix, this thing called a scalar field, which is kind of like woven into the very fabric of the universe. But hold on, before we get too far ahead of ourselves, let's break this down. What are we even talking about with this tensor versus scalar business?
You've got a good point. We've got to make sure we're all on the same page with the lingo, right?
Right. It's easy to get lost in the jargon.
Absolutely. So think of a tensor theory, like Einstein's theory of general relativity, as using a really, really advanced grid system to describe gravity.
Okay, like a superpowered spreadsheet for the universe.
Kind of. Instead of just your regular X, Y, and Z axes, imagine a grid that can bend and warp in all sorts of crazy ways. That's what Einstein used to describe how space-time gets warped, which creates gravity.
Right, like those cool graphics they always show of a bowling ball on a rubber sheet, distorting the fabric of space-time.
Exactly. Now, a scalar, on the other hand, is a much simpler idea. It's just a single number that tells you something specific.
Okay, so like temperature would be a scalar, right? It's just a number that tells you how hot or cold something is.
You got it. Or like your height or your weight. Just one number.
Okay, I think I'm with you so far. So I've got these complex grids from tensor theory and then these simpler single-value scalars. And this new theory, this scalar-tensor theory, is trying to blend the two together. I'm already feeling like I'm back in physics class, trying to wrap my head around this stuff.
It's definitely next-level physics, but trust me, it's worth wrapping your head around.
Okay, I'm trusting you. But seriously, why even go through all this trouble? Why try to mess with Einstein? I mean, his theory seems to work pretty well, doesn't it?
Well, yeah, Einstein's theory is definitely no slouch. But that's the thing about physics. We're always pushing the boundaries, always questioning what we think we know. And believe it or not, there were a few hints, a few cracks in the surface that maybe, just maybe, Einstein's theory wasn't the whole story.
Okay, now you've got me intrigued. What kind of hints are we talking about? Was Einstein wrong about something?
Well, not wrong exactly, more like incomplete, perhaps. For example, there was this physicist, Paul Dirac, a real heavyweight in the field, and he suggested something pretty wild, that the gravitational constant, that big G in Newton's famous gravity equation, might not be so constant after all.
Hold on, a changing constant. That's like saying pi is suddenly 3.2 instead of, 3.14 and a bunch of other digits.
I know, right? It was a radical idea.
A changing constant. It just sounds wrong.
I know, it seems counterintuitive, but that's what made it so intriguing. And it got physicists thinking, hey, what if there is something more to gravity than meets the eye? And this is where Pascal Jordan enters the picture. Now, Jordan, he wasn't content with just adding a scalar field on top of Einstein's theory, like sprinkling a little cinnamon on your morning toast. He introduced this whole new concept called non-minimal coupling.
Non-minimal coupling. Now that sounds intense. What in the world does that even mean?
Imagine this. Instead of gravity just being determined by the curvature of space-time, like we talked about before, this scalar field, it gets in on the action. It directly interacts with the very structure of space-time itself, influencing how strongly gravity behaves at different points.
Whoa, so it's like the scalar field is basically directing traffic, telling gravity how to behave.
That's a great way to put it. It's like a cosmic choreographer making sure everything moves in sync.
Yeah.
Or maybe throwing in a few unexpected twists and turns, depending on the scalar field's mood, I guess.
Okay, my brain is officially doing the twist. I'm looking at this equation here, equation 1.1 from the excerpt you sent. And I'm not going to lie, it's a bit intimidating. Can we try to break it down? What is that Jada thing, and why should we even care about that first term? It looks like a jumbled mess of symbols to me.
You're not wrong. It's not exactly the most user-friendly equation, but don't worry, we can unpack it. So that, Judge, that's our mysterious scalar field, the one Jordan brought to the party. And that first term, the one where you see J hanging out with the curvature R, well, that's the heart of this non-minimal coupling thing. It's basically saying that the strength of gravity, represented by that big G, isn't a fixed constant anymore. It can actually change depending on what this J field is up to.
Hold on, are you saying that gravity, the force that literally holds the universe together, might not be the same everywhere? That's a pretty wild thought.
It is, isn't it? It means that instead of gravity being a one-size-fits-all kind of force, it might be more like a dial that can be tweaked up or down depending on where you are in the universe and what the scalar field is doing.
Okay, yeah, my mind is officially blown. So we've got this scalar field potentially messing with the very strength of gravity. But how does this all play out in the real universe?
Hmm.
Does it change how gravity behaves in a way that we can actually notice? So we've got this idea that there's this scalar field out there potentially tweaking the strength of gravity. But how would we even know if it's really there? Does it, like, leave any fingerprints on the universe that we could actually see?
That's the million-dollar question, right? We can dream up all sorts of cool theories, but we've got to put them to the test. And that's where those experiments with the Greek letter ho come in. You remember the ones that tell us how much the scalar field is actually interacting with gravity.
Right, like that volume knob you were talking about earlier. Turn it up, the scalar field's influence gets stronger. Turn it down, and it's more subtle.
Exactly. So what have those experiments told us so far? Well, I hate to break it to you, but they're pointing toward a more subtle scalar field, a quieter volume knob, so to speak. And one of the big ones, the one that kind of put a damper on things for a while, were those measurements from the Viking mission to Mars.
Viking? You mean those missions to Mars back in the 70s? What does going all the way to Mars have to do with the scalar field messing with gravity? Seems like we could just, stay here on Earth and do our experiments.
Well, sometimes to really test these fundamental theories, you've got to go big. And the Viking missions were big, a really big deal. They were designed to do all sorts of cool science on Mars. But what we're interested in is how they helped us test the predictions of this theory. So one of the things the Viking missions did was measure signals from spacecraft as they were orbiting Mars. And these signals, because they travel at the speed of light, are affected by the gravity of the sun.
Okay, so the sun's gravity can actually mess with radio signals. I never knew that.
It's pretty wild, right? And it's something Einstein predicted with his theory of general relativity. But here's the thing, the Brans-Dicke model, remember that one? The classic scalar-tensor theory? It predicts that if the scalar field is strong enough, it'll actually change how much those signals are delayed by the sun's gravity.
So it's like the scalar field is leaving its mark on how those signals travel through space.
Hmm.
And by carefully measuring those signals, we could potentially see if the scalar field is messing things up, right?
Bingo! It's like listening for a faint whisper in a really noisy room. You have to have a really sensitive ear, or in this case, really sensitive instruments. And when the scientists analyzed all that data from the Viking missions, well, they found that if there is a scalar field out there, it's definitely not making a lot of noise. It's being very, very quiet.
So how quiet are we talking about here? Give me the numbers.
Remember our volume knob for the scalar field? The Viking measurement said that I has to be greater than about 1,000. To put that in perspective, if O were, say, 1, the scalar field would be much easier to see. But with it being so high, it means the scalar field's impact on gravity is really, really weak, really weak.
Okay, yeah, that's a pretty big volume knob. We're talking about trying to hear a pin drop in the middle of a rock concert. So, guess no squished sun then. What a bummer. It sounds like even though this scalar field has been playing hard to get, it's still led to some pretty creative thinking.
You got that right. It's pushed the boundaries of what we know about gravity and forced us to come up with some incredibly clever ways to test these fundamental theories.
It's like we've gotten a glimpse of this whole universe full of hidden possibilities, even if we haven't quite unlocked all of its secrets yet. But you mentioned earlier that the Brans-Dicke model, with its scalar field and all, might just be a small piece of a much bigger puzzle, something even more mind-blowing. What did you mean by that? What other secrets might be lurking out there?
Oh, just some light stuff, extra dimensions, string theory, the possibility that our entire universe is like a membrane floating in a higher dimensional space. Casual Tuesday afternoon physics chat.
Okay, now you've really got me hooked. You're going to have to tell me more about all of that. All right, you were about to blow our minds wide open with some next-level physics. Extra dimensions, string theory, universes as membranes. I'm strapped in and ready for the ride.
Get ready, because we're about to dive into the deep end of theoretical physics. Let's start with this whole idea of extra dimensions. We experience the universe in 3 dimensions, right? Up, down, left, right, forward, back. But what if I told you that our universe might have more dimensions than we can even perceive?
Okay, more dimensions. It's one of those things that I've heard before, but it still makes my head spin trying to picture it. How can there be more dimensions than what we see around us? It's like trying to imagine a new color that's outside the spectrum of what our eyes can detect.
It's a wild concept, for sure. Think of it like this. Imagine a garden hose strung across the yard. From far away, it looks like a one-dimensional line, right? But if you zoom in, if you were an ant crawling along that hose, you'd experience a whole other dimension, that circular dimension that makes up the hose's circumference.
Okay, I can kind of wrap my head around that. So you're saying there could be these tiny curled up dimensions all around us, like the surface of the hose, but on a scale so small we just can't see them.
Exactly. And here's where it gets really interesting. The size of these extra dimensions, how tightly wound they are, might actually be determined by something that looks a lot like our friend, the scalar field. It's as if the scalar field is the cosmic tailor, adjusting the fabric of the universe, determining how big or small these hidden dimensions are.
Hold up, so not only could this hypothetical scalar field be out there subtly messing with gravity, but it might also be controlling the very structure of the universe, how many dimensions there are. This is some serious matrix level stuff we're talking about here.
It's mind-bending, isn't it? And we're just getting started. Let's talk about string theory, the theory that says everything in the universe, all the particles, all the forces are made up of these tiny vibrating strings of energy.
String theory, the one that always sounds like it belongs in a science fiction novel. Tell me that has a role for our scalar field friend as well. It's got it, right?
Oh, absolutely. String theory loves scalar fields. It not only has a role for them, but it actually predicts a really important one called the dilaton.
The dilaton. Okay, it even sounds important. What's so special about this dilaton?
Well, picture this. In string theory, the force of gravity is carried by a particle called the graviton. It's like this tiny messenger particle that transmits gravity between objects. And the dilaton in this picture is like the graviton's partner in crime. It's a scalar field that shows up in the equations and has a big influence on how gravity behaves.
So it's like the dilaton is the puppet master, whispering in gravity's ear, telling it how to act. But why do we even need a dilaton in the first place? What does it bring to the table?
Great question. One of the main reasons physicists get excited about the dilaton is that it might help solve some of the really tricky math problems that come up in string theory. String theory is a notoriously complex beast, and it has this annoying habit of producing nonsensical answers. Things like infinities when you try to do calculations.
Infinities. Yeah, that's not a good sign in physics. Or in my bank account after a shopping spree, for that matter.
Exactly. Not a good look for a theory that's trying to explain everything in the universe. And that's where the dilaton swoops in to save the day. It can actually help tame those pesky infinities, making the math of string theory a bit more well-behaved, a bit more sensible.
Okay, so the dilaton. String theory's knight in shining armor, here to save us from mathematical chaos. But we've done extra dimensions. We've done string theory. You mentioned something even wilder earlier, something about our whole universe being like a membrane.
Oh, yes. You're ready for the grand finale, the ultimate head scratcher.
Yeah.
Brace yourself, because it's brain world time. Imagine, if you will, that our entire universe, everything we can see, touch, measure, is actually a giant sheet, a brain floating in some higher dimensional space.
Okay, now my brain officially needs a reboot. So you're saying our entire universe, all those billions upon billions of galaxies, are just chilling out on a cosmic sheet, like a cosmic, bed sheet or something.
It sounds crazy, I know, but that's the basic idea. And what makes it even crazier is that these brain world scenarios might naturally give rise to, you guessed it, scalar fields. These scalar fields could be tied to how the brain is embedded in this higher dimensional space, how it interacts with other brains if they're out there, and that opens up a whole Pandora's box of wild possibilities.
Okay, I'm going to need a minute to process all of that. We've covered so much ground today. Everything from the Brans-Dicke model to extra dimensions to string theory and now brain worlds. It's a lot to take in. So let's bring it back down to earth for a second. Why should we even care about these mind-boggling ideas, these wild theories? I mean, they're fascinating, sure, but are they just theoretical curiosities, or could they actually tell us something real about the universe?
That's the beauty of theoretical physics. It's about pushing the boundaries of what we know, about asking those what-if questions that lead us to new and unexpected discoveries. These theories, even if they sound like something out of Star Trek, force us to confront the deepest mysteries of the universe, the nature of gravity, the origin of our cosmos, and ultimately our place in the grand scheme of things.
So we're not just playing mental gymnastics here. We're trying to peer behind the curtain of reality, to glimpse at the machinery that makes the universe tick. And even if we don't have all the answers, heck, even if we haven't even been asking the right questions yet, it's that journey of exploration that makes it all worthwhile.
You said it. And who knows, maybe someday, these seemingly outlandish ideas, these mind-blowing theories, will lead us to breakthroughs that completely revolutionize our understanding of the universe. After all, Einstein's theory of general relativity, the one that describes gravity as the curvature of spacetime, seemed pretty crazy when it was first proposed.
It's a good reminder that we should never stop questioning, never stop exploring. The universe is full of surprises, and the more we learn, the more we realize just how much more there is to discover. I want to thank you for joining us on this wild ride through the weird and wonderful world of scalar tensor theory and beyond. We've just scratched the surface here today, folks. If you're hungry for more, if you want to really dig into the nitty-gritty details of these incredible ideas, I highly recommend checking out the scalar tensor theory of gravitation. And on that note, we'll leave you to ponder the mysteries of the cosmos. Until next time, stay curious.